Hello, respectful teacher and classmate. We ADSH group. Today we'll present one IEEE research paper on networking. The paper has the title, Realizing Dynamic Networking Slice Resource Management based on SDN Network. Background, motivation, and networking development training. Modern networking technology is evolving rapidly. We can see new generation of the wired and wireless networking like 5G Starlink, quantum communication, and more. And the booming of the new and advanced application, virtual reality, smart city, and more. Networking management, because the booming and the new generation introduction of networking is facing tremendous challenges. Overwhelming new connected device, skyrocket data and traffic, strict requirement on network latency and high throughput bandwidth and dynamic loading. In order to address above challenging in networking management, network slicing based on SDN virtual networking function is potential solution. With that approach, we can achieve flexible and scalable management. Is also cost efficient and well balanced between centralization and distribution. Next page, Michael, please.
Hey, so I'm Michael, and this is going to be an overall paper summary. Basically, IoT devices and other network devices in various fields will require many different types of network service features, such as mobility, security, high bandwidth or throughput, low latency, reliability, control strategies, and that's just to name a few. There's a billion different permutations that any one device could need over another. So in order to meet all those requirements above, the authors developed a dynamic network slice resource scheduling management method based on SDNs with time-varying characteristics. A prototyping system was detailed and implemented in the paper for validation, and by the end, the effectiveness of the system was demonstrated using an electronic fence demo on a farm that we will detail later on in this presentation. Next slide, please. So what is dynamic network slice resource management? Basically, it's the concept of splitting up one big network into many individual virtual software-defined networks. This is done by identifying and classifying all types of different devices connected to the network, as well as whatever traffic is coming in that is meant to go to those devices and separating them based on classifiers. This allows us to allocate resources dynamically to different virtual networks, depending on what's going on in real-time events and what sort of prioritization needs to happen for the most efficient network overall. And finally, this removes the need for many physical networks, since you can have just one big virtual network that splits up different network functions into slices rather than multiple different physical networks. We have two images on the right here. The top image basically illustrates what I was just saying. So the top image here has 3 physical networks. Instead of having these 3 separate networks, we could have one big 5G network, and all the different slices will correspond to different services or industries. In this case, they broke it down by communication internet, logistics, and emergency calling. The bottom image here shows a network slice pairing function. So when network traffic comes into the system, there's a slice pairing function or algorithm which classifies the data and which slice it belongs into. Here we could see things such as radio access and fixed access network slices coming into the slice pairing function and then divided up into which core network slice they belong into. These core network slices have at least one set of network functions, and that's generally what defines the purpose of a network and why it's different from the other network slices. So resource management using network slicing. Here, the team used Ryu and Python in order to build their overall controller and software architecture. Using OpenFlow's meter entry structure, they were able to categorize different devices and split them up across network slices. This allowed resources to stay flexible and give and take between network slices as needed. The exact example used, again, will be touched on later in this section, but for now, let's talk about how the team described their algorithm. Basically, either the OpenFlow virtual switch or a subscriber would pass in data consisting of either initial data for setup or some sort of event trigger that has happened. This data would then be evaluated to either set up a network slice or make adjustments to an existing slice. Their algorithm would evaluate the event and then either accept or reject the resource management assignment or adjustment. What this really means is that the system is constantly reallocating resources based on new connections coming in and or events that are happening within the overall network in real time dynamically. So here's a simplified system architecture I created in Photoshop to help explain the overall concept and process. First, you have a software-defined virtualized switch being controlled, in this case by a Ryu SDN controller. When, say, something like a web server passes in data, it goes through the switch and into the slice pairing and resource management algorithms. Depending on the data, it'll be paired with the appropriate network slice and possibly cause resources to be reallocated depending on what's going on. Then that data gets passed into its respective network slice. The experiment that the team carried out only detailed a camera network slice, and the rest were just called others. So I made a more general example with a little bit more detail here, just to better illustrate this point. In this case, we have 3 network slices, one for mobile phones, say doing just texting and IM and web surfing, one for gaming, and one for some security system. The slices will be given the following resources due to their needs. IM and texting is a very low bandwidth operation, so for this example, I only gave it 10%. Then the security system may need to accurately monitor and report events, so it might need a little bit more to stay connected and ensure that a connection doesn't drop, so I gave it, say, 30% of the network. Finally, a gaming slice would require a lot to ensure a low latency environment, so here we gave it 60%. This is just one possible example, but this could be expanded upon to have any number of network slices with any number of network allocation, and these could all also change dynamically. Next slide. So here, the team, in order to show and prove what they have done in the paper, they carried out a demo on a farm. So basically, they set up cameras on a farm and gave the cameras their own network slice, and everything else, they didn't detail this, but everything else had their own separate network slices. When things were normal, recognized farm staff were in view of the cameras. They're able to classify people, and those people were normal staff. This was a normal event. So during this, the camera slice was given 50% of the resources. However, when an illegal event happened, say some sort of trespasser or a person walked in frame that was not recognized as a farm staff, that triggered an illegal event in the system. What would happen then is that the resources for the camera slice was bumped up to 80%. This was to ensure that no connection is dropped and that they could track the trespasser correctly. Finally, when the illegal event ended and the trespasser left the camera frame, it was reduced back to 50%. This all happened dynamically and in real time, proving the overall concept the paper sought to prove. On the top image here, we could see that over time, the resources between the camera slice and all of the others that weren't detailed were about 50-50. However, when an illegal event happened, that's when we have that hexagon looking pattern in the graph, which basically shows us that the camera slice spiked up to 80%, everything else was given 20%, and then after the illegal event, it spiked back down and they returned back to about 50-50. And then finally, you could see the same sort of concept reflected here in the bottom image. In this pie chart, initially everything was 50% camera and whatever else is on the network got the other half of the resources. But when an illegal event happened, it spiked up to 80%. So this kind of proves the overall concept and that it is possible to dynamically allocate resources based on real-time event triggers in a network.
All right, hello everybody. My name is Douglas, and I will be covering the strengths for this research paper. So for paper strength number 1, I'll cover the technical evaluation. So the authors identified a problem, which was mobile broadband usage, massive IoT, and mission critical IoT. All 3 of those are pretty much going to equal an unprecedented network demand. So comparing that to 4G utilization, 4G primarily handles broadband usage. So the 5G network will bring along much more demand, which will require customized services, lower latency, and 100% reliability. The proposed solution that the authors came up with was to develop an end-to-end network slicing capability utilizing software-defined networks. So on the right side of the screen, it kind of depicts what was mentioned earlier. You have a massive network that is going to be divided up into different slices. This example shows a broadband slice, mission critical IoT slice, massive IoT slice, and a voice slice. And that's going to cover various functions such as internet usage, entertainment such as Netflix, automation, looking at self-driving vehicles or factories, medical services, smart cities, which would involve potentially monitoring roads, giving live updates to traffic information, and then voice and communication. So this will basically allow for a dynamic network resource allocation. Next slide. Paper strength number 2 covers the system architecture. The system architecture was built using their own created SDN, which was done through the reuse software framework. So on the left side is an actual graphic that shows the network that the authors used. So at the very top, there's a video and web server, which was used to host video information. That was connected to their Ethernet RT188T, and that was the software-defined and virtualized switch. So the switch was also connected to the SDN controller, and that resided on a laptop computer, and that was, of course, with the reuse software. Moving further down the graphic, it shows the software-defined and virtualized access points, which was being handled by the ASUS RT AC68U, which was a wireless router. And that kind of shows the open flow protocols and the virtual access points, which eventually fed down to the very bottom of the graphic. And on the left side is a Raspberry Pi, which was a computer device they used for camera connections. And then the right side of that graphic shows just general internet usage. All right, so the network management authority was delegated to the controller, which again, that resided on the laptop computer. The RT188T and the RT-AC68U, so the switch and the router, those automated the end-to-end network slicing, which used open source software. So all the way on the right side of the screen, some of the software that they used, starting from the top, was the reuse SDN, which a lot of us are familiar with. So they use that to separate the control plane of the router from the data plane. Within that, they use Python to complete network architecture, which would eventually implement the network slicing. The protocol used was OpenFlow, which created flow entries, allowing for dynamic adjustments of network resources. And then they used Open 5G to create a simulated 5G network. So adding to that, they did use the Zixtel LTE 4506, which was a mobile hotspot. And so the prototype that they built was in an environment that did not have normal internet connectivity. And this is what they used to create that internet. Next slide. Okay, so paper strength number 3. This is going to be the usage case and the test results for the prototype that they did. So on the very top left of the screen, there's a camera, and that camera is monitoring a fence. So the fence shows a safe activity, which has a person highlighted. So the IoT device camera observes a person, and at this stage, the controller only provides basic bandwidth resources to the camera to perform stable identification images. These are basically still frames. It doesn't say how many per second, but I would imagine a very low amount. And so moving to the right side of the screens, the network's resources are evenly divided between the web slice and the camera slice, which shows 50% down the middle, and the right side of the screen shows a graph, and both services are using 50%, which is what has been allocated to them. Now, when an illegal event happens, such as a suspicious person approaching the fence, the IoT device camera observes a suspicious person, and at this stage, the controller performs dynamic network slice resource rescheduling, which is going to redistribute the network resources in order to meet the demand of the camera, which the camera is now demanding more bandwidth because it's going to deliver more frames per second, which would be full video. So moving to the right side of the graphic, you see that the pie chart is growing for the green, which is the camera resources. However, it is shrinking for the other devices on the network, which shrinks down to 20%. So on the very bottom right, again, it shows the algorithm that they use, which is a flow chart. Just to recap, so the network slice initialization, it's the data is being evaluated and passed to the controller. And if there is a resource management requirement to up the bandwidth for the network slicing, then it is done. Otherwise, the network slicing stays the same. So in this prototype, they properly demonstrated that they were able to dynamically change the bandwidth required, and the network was only sliced into two. So you can imagine how using this architecture, it could definitely grow and meet the demand for 5G.
Perfect. Now I will cover paper waitlist. Paper waitlist number 1, uncommon usage case for slicing. As you can see from the diagram in this page, modern network slicing technology is a network architecture that enables the multiplexing of virtualized and independent logical networks on the same physical network infrastructure. Each network slice is an isolated end-to-end network tailored to fulfill diverse requirements of particular application. In the paper, the author built a prototype system for slicing, scheduling, and implementation, and select the electronic fencing as a usage case for evaluation. This seems too uncommon for slicing technology evaluation, as only throughput feature is tested and verified. It will be more valuable to select a typical usage case like the LiDAR sensor or autonomous driving, which will test not only network bandwidth throughput, but also latency, availability, reliability, and other critical features. Because the slicing is meant to meet all kind of network device in all kind of situation, like the broadband, mission critical, and other applications. The design implementation seems not so complete from technical breadth perspective. Paper waitlist number 2, network slicing technology and application. As you can see on the diagram here, for network slicing architecture, the network slicing architecture can be considered as composed of 2 major blocks, one dedicated to the actual slicing implementation, and the other dedicated to the slice management and the configuration. The first block is designed as a multi-tier architecture composed of 3 layers: service layer, network layer, and the infrastructure layer, where each one contributes to the slice definition and the deployment with distinct tasks. The second block is designed as a centralized network entity, generically used for network-like controller that monitors and manages the functionality between the 3 layers in order to efficiently coordinate the coexistence of multiple slices. In the paper, it neck detail for service layer description. There's not much detail on control flow for slicing either. And we don't see much detail for slicing orchestration function as well. Paper waitlist number 3, SDN design and implementation. SDN is essential a centralized networking paradigm in which the network intelligence is logically centralized at one or a set of control entity, where the data forwarding plan is simplified. SDN contains of 4 panels: data panel, control panel, application panel, and management administration panel. Between each panel, there's a defined communication interface. As you can see, there's a northbound interface NBI, and there's a southbound interface SBI. They also have a west-eastbound interface in the block diagram. In the paper, there are also few to describe SDN application panel design in details. It's unclear where loading balance software module locates. It's also unclear how application panel react to process slicing request. Paper waitlist number 4, SDN design and implementation. As shown in the previous page, architecture, the management and administration panel is recently considered by ARMF and IETF. This plan is responsible for all actions related to provision and monitoring of the networks. In this paper, there's not much description for this panel design. There's no data of testing for this panel function either. Paper waitlist number 5, network function virtualization, NFV. NFV is essentially the relocation of network functions from standalone boxes based on dedicated hardware to software appliance running in the cloud environment or on general purpose commodity server. By using NFV, each conventional network function is now running on a virtual machine. They can be one-to-one mapping model or decomposed into smaller components. In the paper, the author briefly mentioned NFV in section 2 only. It's unclear whether NFV has been fully implemented in the prototype system. It's also unclear how SDN and NFV interact each other in the prototype system. Michael?
So in conclusion, the concepts presented in this paper seemed incredibly useful for the next generation of network management. Splitting up a network into slices and then dynamically allocating resources yields a high network efficiency. Some possible slicing algorithms inspired by the paper that we thought of were maybe something like directing IMs and video calls to the right devices on a broad 5G network by perhaps limiting the search for the destination of that traffic to only the IM and video call slice, or maybe only the mobile phone slice. Another possible example would be directing gaming traffic to the right console and then also prioritizing network resources based on the game being played. For example, something like action games generally need very little lag and much lower latency than somebody playing online chess on their browser. And finally, one third example we could think of was dynamically allocating more resources to cameras to meet tight requirements of latency for something such as autonomous driving.
Okay, that's the end of our group presentation. If have any question, please raise your concern in Canvas. We will try our best to answer you there. Thank you.
Thank you.